Cycle 3, Lesson 11. In this lesson, we are going to come back to exponential and logarithmic functions, and we're going to start working with them in an algebraic form. So let's begin by reviewing what we know about logarithms so far. First off, let's start with an exponential function, y equals b to the x. Remember, b is the base, e is the exponent, y is called the argument. Together, it's an exponential function. If we want the inverse of that, then as with anything, we can take the inverse by switching the place of x and y. However, we don't usually write functions in this way, so the more common way of writing x equals b to the y is y equals log the base of b x. These are equivalent, and this is what we're talking about here, though. We're talking about y equals log base b of x. So this function has a domain of all real numbers, but x has to be greater than 0. It has a range of all real numbers, no restrictions. It has an x-intercept of 1. It has a vertical asymptote at x equals 0. And all of this is true, and we know it's true because it's a reflection of the of y equals b to the x in the line y equals x. In other words, it's again the inverse of y equals b to the x. Inverses are always reflected in the line y equals x when we graph them. So here is the line y equals e to the x. Sorry, y equals x. They're all reflected in the line y equals x when we graph them, in case I said that wrong before. So the red one is the exponential function, and we're more familiar with exponential functions probably at this stage, but we do know certain things. We know that they always have a y-intercept of 1, because anything to the exponent 0 equals 1, and this red graph has a domain of all real numbers, it has a range of all real numbers greater than 0. It has a horizontal asymptote in the x-axis. If we reflect all that on the diagonal line y equals x, that's where we get the features of the logarithm, y equals log base bx. That y-intercept of 1 becomes an x-intercept of 1. That horizontal asymptote of the x-axis becomes a vertical asymptote of the y-axis. The domain of the exponential function, all real numbers, becomes the range of the logarithmic, all real numbers. And the range of the exponential function, the red one, which is only greater than 0, it becomes the domain of the logarithmic, only greater than 0. This is growth, okay? So this picture we're seeing here is increasing on the domain when b is greater than 1, and we call that growth, whether it's exponential or logarithmic. So going from left to right, things are going up, in other words, on the y-axis. If we look at this one's decay. It's decreasing. They're both decreasing on the domain. And again, the red one is the exponential function. The blue one is the logarithmic function. And again, it's just a reflection in the line y equals x. They both still have y-intercepts. Well, they don't both have y-intercepts. The exponential function still has a y-intercept of 1, and the logarithmic function still has an x-intercept of 1. So these are some things that we already know, or should know, about logarithmic and exponential functions. So if I want to graph y equals log base 5x, I know a few certain things. I know it's always going to have an x-intercept of 1. I know it's going to have a vertical asymptote on the y-axis, but to know specifically what it looks like, let's go back to what we know better again, which is exponential. So the inverse would be y equals 5 to the x. So if I think about what that graph's going to look like, it'll have a y-intercept of 1. when x equals 1, we'll have 5 to the 1, which is 5. And then when x equals 2, we'd have 25 for a y, which goes off the graph very quickly. If we put negative 1 in for x, we get a y value of 1/5, because 5 to the negative 1 is equal to 1 over 5. So we can see what our exponential function looks like. And then we can just invert those points to get a better idea of what the logarithmic function looks like. So we already saw that we got the x-intercept as 1 because we had a y-intercept of 1 on the exponential function. If I take this point here, switch the x and y coordinates, I get 5, 1. And I have a vertical asymptote on the y-axis. I have a point 1/5 negative 1 because I'm switching the x and y coordinates here. And we can see that the graph should look like this. Again, it's just reflected in the line y equals x. Okay, so if I want to be able to graph these, it's great to be able to picture the original exponential growth graph, but I don't necessarily want to be able to required to graph it first and then do a reflection of it. It's good if I can get to a point where I can just mentally visualize the exponential graph and then reflect it. So again, we know that if I want to graph y equals log x, that's common log. It's the same as it's got an implied base of 10. So the exponential function that's the inverse of this would be y equals 10 to the x. So again, we're going to have a y-intercept of 1. We're going to have a vertical asymptote on the y-axis. But let's imagine if I put into y equals 10 to the x, if I put the number 1 in for that x value, then 10 to the 1 is 10. So on the exponential function, I'd get the point 1, 10. And then if I flip the x and y around, I'm going to get the point 10, 1, which is going to go on my logarithmic graph. And if I put negative 1 in for the exponential function, y equals x 10 to the x, put negative 1 in there, I'm going to get 1/10. So if I go switch those around, I'm going to get 1/10 for my x coordinate and negative 1 for my y coordinate. So again, I can get points, and so I could actually graph it. I'm just trying to illustrate that it's good to be able to visualize these things so that we can go straight to graphing the exponential, the logarithmic function. Obviously, after we work the log functions enough, we won't even need to do that, but that's a good intermediate step. All right, so the domain of the blue graph in each case, the logarithmic function, is all real numbers greater than 0 because there is that vertical asymptote. So for both of these, it's got the same domain. The range actually goes up and down forever. I know it looks like it's flattening out, but it is constantly going up, and it's never going to stop going up. So the range is all real numbers. No restrictions for both of them. I seem to be missing something here. Okay, rather than stop this video, let me just see if I can grab it from somewhere else. Okay, let's try moving it. There it is. Good. All right. The logarithmic function is defined as y equals log base b of x, or y equals the logarithm of x to the base b. This function is defined for b greater than 0 and b cannot equal 1. Examples of notation rewrite in logarithmic form. So we've seen this before, but here's just a quick review of it. This is exponential form, and there's three parts. We have we'll call this the argument, the base, and the exponent. In logarithmic form, I'm not changing this to an inverse anymore. I'm rewriting something that is equivalent. So I just need to put things in their appropriate places. In logarithmic form, the exponent is isolated. So 4 equals the log with the same base, which is 2, of the argument. So I'm going to have a bunch of arrows going everywhere, but at least there'll be different colored arrows, so that will help avoid confusion, I hope. Okay, so all the components are still here, they're just rearranged, and this is equivalent. So what I just wrote here, 4 equals log base 216, is really saying that 4 is the exponent that you must put on 2 so that it equals 16. Or as a question, if I was to take away this and just say, make this into a question, that's supposed to be a question mark, and say, what does log base 216 equal? Well, then really I'm asking, what exponent do I have to put on 2 so that it equals 16? And the answer is 4. So we've done it before. Let's just go through these again, identify the different parts. And it doesn't matter which side of the equal sign we write it on, so maybe I'll go to switching it. So the base was, the base was n, the argument was m, and the exponent was 3. So I've isolated the exponent. Now these ones are in logarithmic form already, so I'm going to go backwards. The base is 3. Oh, this one isn't an equation, sorry. Got ahead of myself. This is literally doing what I was just talking about. It's asking us to evaluate it. This is saying, what exponent do I have to put on 3 so that it equals 81? Well, 3 times 3 is 9. That's 3 squared. If I do 3 to the exponent 3, that's 9 times 3 is 27. If I multiply by 3 one more time, it equals 81. So if I put the exponent 4 on a base of 3, it equals 81. So log base 381 equals 4. This one is a common log, so it's got the base of 10. So it might be easier to picture it as a fraction here. 0.01 is the same as 1/100th. And in fact, maybe I could just rewrite this as a base 10. That's one strategy, right? So I know that 1 over 100 is the same as 100 to the exponent 1, negative 1. But I know that 100 is just 10 squared. So this, when I use powers of powers, exponent law, and multiply those together, I know that 10 to the negative 2 is equal to 0.001. So what exponent do I have to put on 10 so that it equals 10 to the negative 2? Well, obviously the exponent is negative 2. Now I showed a long way around to get to that. You might have jumped straight to that answer in your mind, and that's fine. I'm just explaining how we can think about it. We've already talked about what a common logarithm is, so let's review as well. If it doesn't say what the base is, it's assumed to be 10. Here's another one, so going backwards, now if we want to write it from logarithmic form to exponential form, the same rules apply as above. I should be able to switch back and forth easily. So in exponential form, my base is still 4, my exponent is 3, and it equals 64. And that's true, right? 4 to the exponent 3 does equal 64. Of course it's true, it has to be, otherwise we wouldn't be allowed to write it. In B part, the base is assumed to be 10 for a common log, the exponent was y, and x is the argument, so 10 to the y equals x is what this one is looking for. Now, a few times in previous lessons I've talked about something called the change of base formula. So you're probably familiar with it already, but here it is. Some calculators don't have the option of putting whatever base we want on a logarithm. Some of them just give us the common log. But that's not a problem, because with this formula we can calculate any logarithm. And what it says is, if we have a log with a base b and an argument of m, if I just take the common log of m and divide it by the common log of the base, it actually will give us the equivalent answer. So let's keep that in mind. Well, actually, let's just do one right now. Let me make one up. Let's pick some random numbers. Let's pick a base of 7 and a argument of 31. Hopefully it's clear that there's no whole number exponent that I can put on 7 that's going to equal 31. This is going to be a decimal. So using the change of base formula, I could just do the common log of 31 and divide that by the common log of 7, and that will give me my answer. 31 log divided by 7 log equals 1.7647, so let's call it 1.765. So what does that mean? It means if I put the exponent 1.765 on a base of 7, it should equal 31. Let's try it. Now I rounded, so it won't be exactly, but 7 to the exponent 1.765, I think it was, equals 31.01, etc., and that's just a rounding error. Another law about logarithms that we can use, and it's sort of equivalent, it goes along with the exponent laws, since logarithms are just exponents powers written in a different form, says that if I have a log with an exponent built into it, that was supposed to give me a nice box. Let's try one more time. There we go. So if I have something like log base b, and the argument is x to the n, so I've taken the log of a power, I can actually move that exponent down in front of the logarithm and just multiply by it. So that's really helpful, because it's much easier to deal with multiplying things. Often we're trying to isolate our variable, which is x in this case, and it's a lot easier to isolate it if I don't have that exponent on it. So we can use this to help us out. So let's take a look at some examples. For this one, we've got the power 9 to the 4, and so using the power law of logarithms, I can bring that 4 down to the front, make it a multiply, and we could use the change of base formula, but hopefully this is pretty easy to solve in our minds. If we just ask ourselves, what exponent do I have to put on 3 so that it equals 9? Hopefully the exponent 2 will immediately come to mind. So 4 times 2. Log base 3, 9 is equal to 2. And I just multiply that by 4, so this equals 8. If I bring the 5 down here, because that's my exponent, then I can ask myself, what exponent do I have to put on a base of 2 so that it equals 8? 2 to the exponent 3 equals 8, so it would be 5 times 3. So this one simplifies to 15. Bring the 2 out front. What exponent would I have to put on a base of 10, because this is a common log, to equal 0.001? I'm going to go with -3. I could change it to a fraction like I did in a previous example, but since it's base 10, I also have the option of just moving the decimal. If I move the decimal, 3 places to the right, then I'll get just 1, and that would be -3 as my exponent. I'm not sure if that's a clear way of explaining it, so let's just actually type it in. Maybe that's easier. 0.001 -3. So we get the same way. We can type that one straight in. So it's still not done, though. If you 2 times -3, so -6. Now remember, roots can be written as exponents as well. So we could rewrite this as log base 5 of 125 to the exponent 1/2. So a square root can be expressed as an exponent as 1/2. And then I can just bring that 1/2 out front, and then I can say what exponent do I need to put on 5 so it equals 125. Hopefully it's obvious it's 3, but let's just try the change of base formula for practice. So let's pretend that we didn't recognize it, but of course we do. Log 125 divided by log 5 using the change of base formula. So we got 2.9069, but I don't care about the in-between stage, because I'm then going to take the log of 5, which is 0.6987. All I care about is the end, which when I divide those two out, I get 3, which is hopefully what was obvious. 5 to the exponent 3 does equal 125. But we're not done. We still have to multiply it by 1/2. So it's going to be either equal to 3/2 or 1.5. Same thing. All right, there's a summary of some of the things that we just talked about, and here's one last example. Suppose you invest $100 in an account that pays 5% interest compounded annually once per year. The amount in dollars in the account after any given time t is given by this formula. So they've already given us the formula. We don't even need to set it up, but just confirm that it does make sense to you the way it looks. Predict how long it will take to the nearest year for the amount in this account to double in value. Give a reason for your estimate. Well, the reason is going to be the calculations we show. So if we take this formula, and I want the $100 is what we started with. So in order for $100 to double, we're going to have to end up with $200. So I'll put 200 in for A. That's our final amount. And I want to find the time in years. Now, since the interest is only compounded once per year, whatever the exponent t is going to be the number of years. I can simplify this, and I should simplify this, by dividing both sides by 100. And so that reduces to 2 equals 1.05 to the t. So it doesn't matter even what amount of money we started with. We could have started with $1 and then doubled it to 2, or $1,000 and doubled it to 2,000. When we reduce it, we're always going to get down to this same formula, right? It's just how long is it going to take for 1.05 to become 2 as a power. Here's a case where we can now, we want to get what t is. We've used Desmos in the past. We could use guess and check, but here's the most elegant way. Let's rearrange it and isolate t. If I bring if I rewrite it in exponential form, I was about to try and bring t down, but it's not in the correct form. This is where the beauty of logarithms lies. Now we can rewrite it in a form that will allow us to isolate t. So rewriting in logarithmic form, I have t, exponents always isolated, equals log base 1.05, because the base stays the same whether it's an exponential form or logarithmic form, of 2. This is one that I would want to definitely use the change of base formula for if I don't have an option on my calculator to put my own base in. So it would be log 2 divided by log 1.05. And I got 14.2. So the way we can interpret that is that it takes almost 14 years. Sorry, not almost 14 years, just over 14 years. I'd say almost 15 years. It takes more than 14 years anyway. At 14 years, we won't have doubled yet. But at 15 years, we will definitely have doubled our money. And that's the end of this lesson.